I thought I would just quickly cover the things that are available right now if you went in the clinic. So there's two tissues that you can go that are FDA approved and people get. The first one is skin. I'm sure you've heard of skin grafts. If you get a large burn on your arm, say like in the picture over here, they'll take skin cells from a part of your skin that is not damaged, grow them up in the lab on top of a material, and then take that grown piece of skin and stick it back on the injured site. So this works. It has worked really well. It was an early success in tissue engineering. There's a lot of companies now making these kinds of things. The big thing to keep in mind is that skin is relatively easy. So it is a thin material. You don't need blood flow. Skin cells, if you take a few skin cells from one area that's not damaged, will proliferate fairly well in the lab. So you can make lots of cells from just a few cells that you took off of the patient. The other one that's available is for cartilage. So cartilage is that tissue on the top of load-bearing joints. They kind of cushion your bones so it doesn't hurt when you walk around. And if you have arthritis, you know that the cartilage goes away and then it hurts. So cartilage is avascular. There's no blood flow anyway. It has very few cells. It's mostly protein and other molecules making the tissue. So the way this technique works is they take some of the tissue from the non-load-bearing part of your joint, so part of the tissue that's not getting mechanically stimulated, take the cells out, grow them up in the lab, put them in a material, and then you stick them back in the joint. And that has had some success. And you may have heard athletes tend to get this a lot, so like NFL football players after they get injured. But it has some success in, depending on who you ask for long-term potential. But that's about it. So that's what's approved. There's certain things like bladder tissue engineering that's getting near going through clinical trials and things like that. But these are relatively easy, again, tissues. They don't have the blood flow and the things like that you need to do. And so most of the things that are facing the current biomedical engineering field in terms of tissue engineering is how do we get these things that we've made to integrate with the host tissue? And if I'm going to make a thick piece of tissue or a whole organ like a kidney, where am I going to get cells enough from to make this big structure? And of course, if it's a big structure, how do I get blood flow into that structure? And this is where stem cells come into play. Obviously, I can't make a whole kidney, a whole liver by taking, a similar size hunk out of a liver. It doesn't work that way. So you need some kind of cell that will proliferate and then eventually differentiate the way you want it to go. You can get them to differentiate in the lab, but there's questions, of course, as to whether you want to wait until they're fully mature or whether you implant them before they fully mature and you implant them in the host and hope they continue maturing in the host. But overall, that's where stem cells have the greatest promise for tissue engineering.